Okay, so guys, we're at kind of an interesting point here. Frankly, it's our first time, so let's talk. So we just took a test, which is the way we end units, right? And so now we're beginning the next unit. Kind of makes sense, and we do this enough, and then it's May and we get to go away for the summer. But guys, this is the way the class will always progress. So when you come in from a test, we'll typically have a conversation kind of like this, where we'll sort of tee up the next unit, give you a sense of what it looks like. And guys, frankly, a lot of times when you come back from a test, I'll hand your test back to you. They're not done, and I'm not really sure how much to say about this. I'm just going to say it. I really thought these were going to be really easy to grade. That I was just going to sit down and it was going to be this big euphoric experience where you all, went into lab and find the mass of the metal, add some water to a graduated cylinder, read its volume, add the metal, reread the volume. It was just going to be smooth sailing, and it was just going to be perfect papers, and holy buckets. I sat down to grade your labs, and it felt like a surgical procedure where I was like going, please let me find something that's right, because it's not there. And after doing like 7 or 8 of these, I considered gouging out my eyes. And then frankly, rather than having a Shakespeare moment, I just stopped. And I'm sort of regrouping emotionally to sit back. Sorry, this is probably not what you wanted to hear. But, whoa. Yeah, so guys, here's the thing though. I have to believe that the law of averages is going to say that your overall scores will be okay, because 15 points was off the lab, 75 points was off the bubble sheet. From looking at your bubble sheet scores, they weren't bad, but we've got some work to do in terms of communicating lab work. And so, frankly, I just had to quit. I gave up. You beat me. And so, sorry. And that could have been, it could have been. I know. Okay, so all of that to say, guys, when I see you Thursday, I don't know how I'm going to do this, because today after school I'm leaving immediately for a concert up at Red Butte. Do you guys know Mark Knopfler? To Mark Knopfler? It's going to be an amazing... Do you guys know Mark Knopfler? He's the lead singer of a band called Dire Straits. He did the soundtrack for Princess Bride, which we've all seen. Yeah, so he's an amazing folk guitarist. Anyway, I'm going to see Mark Knopfler. And then tomorrow's parent-teacher conferences, then Thursday, 3 to 7. And so I'd like to believe I'll get these done for you Thursday. So guys, let's talk about the way this is going to go then. So today we're going to talk about the stuff that you have in front of you, classifying matter, and talking about changes. Then guys, on Thursday we're going to do a lab. You're going to like this lab. It's completely qualitative, which means what? No math. It's all observation and description. Frankly, it's a nice break from all the tedium of significant digits and things like that. So we're going to do a lab on Thursday. Then guys, this day for many of you is going to be relatively redundant. Well, not redundant, but review. We're going to talk about subatomic particles. Finally, this class is going to start to feel like chemistry. And we're going to grab our periodic tables, which many of you still don't have, and I'll make allowance for that. We're going to grab our periodic tables and we're going to figure out what atoms are made of. Then guys, on Wednesday, we're going to go a little bit deeper into that and talk about some of the things that happen that are different relative to that. Then guys, the 25th will be another lab, and then amazingly enough, 2 weeks from today is our next test. It's a very short unit. So guys, with that said, can you see the stuff in red, or is that too small? Yeah, so let's talk about, just a second, let's talk about retests. So guys, the way that this will always go down is that after you get your test back, whatever week it is in which you get your test back, whether that's a Thursday or a Monday or it doesn't matter, whatever day you get your test back, the following week will be retests. And we will always try to give you 3 days to do retests. But now we have 3 chemistry teachers. So that means we can each take a turn and you don't have to retest with me. So Tuesday after school will be retest with me. Wednesday after school will be with Miss Call. And then Thursday after school will be with Mr. Hart. You can go to whichever teacher you prefer. Not if you prefer, whatever day works better for you. But guys, these are all necessarily after school. If that doesn't work for you, you've got to come and make other arrangements with me and we'll always make something work. Could be Pride, but that's by appointment only. This is the agreed upon idea. Remember guys, retests come at a 10% deduction unless there was a reason, like you were sick, unless there was a reason you missed the test that was unavoidable. So when you turn in your test, remind me you were sick. Guys, other than that, it's a 10% deduction for the retest. So there you go. Tatum, what are you going to say? I always at least 2, because you can't get an average off of 1, right? The thing that's the problem is that first quarter we spend so much time just doing lab safety and lab checkout and get to know you and all this. This first unit is unusually long because of the weird stuff we do at the beginning. So sometimes we don't get in a 3rd test first quarter. Yeah, I said that right. But normally it's 3 tests a quarter. So yeah. So guys, anything calendar? Y'all good? We're okay? We're good? Okay. So guys, here's what you need to do then. Grab this sheet of paper that I gave you that has the triangle on it. I called that thing a pyramid in front of a math teacher and they freaked out because pyramids are 3-dimensional. Because math teachers care about stuff like that. And guys, here's what we're going to do. If you grab that, not the homework is the one that says classification of matter. If you grab this dude, guys, let me explain to you the way today is going to go down. What we're going to do is today is kind of like language lessons. You are going to learn to communicate effectively in a chemistry setting so that when we go into lab on Thursday and you say, hey, I need a beaker full of that compound, it is actually in fact a compound. Or where's that sample of the element? Or what's in that solution? Or how did you make that heterogeneous mixture? Oh boy. See, guys, there are terms that you need to be able to understand so that you can communicate intelligently with other people that are trying to do chemistry. So, guys, today is kind of like language lessons. Now, let me tell you the way this is going to work. In just a minute, this triangle is going to magically appear on the board. And guys, all of your terms and concepts and things that you need to know are going to be structured around this triangle. And mine, like yours, has this white space all around it where you can take notes. I'm not trying to be like a dictator here, but guys, what I would encourage you to do is not only write down the things that come up on the screen, but write them down where they come up on the screen, because I figured out a way to make it all fit. You know what I'm saying? Like that. Exactly. See, you got it. But guys, what we need to do first is we need to start with the end in mind. So guys, allow your eye to fall to the bottom of the triangle. And you'll notice that if you look at the bottom of the triangle, there are 4 terms down there. Reading from left to right, it goes element, compound, then a homogeneous mixture, which you'll find out in a minute we call a solution, and then off to the right, a heterogeneous mixture. Guys, those 4 terms are the end game for today. You've got to be able to distinguish between them. Here's how you're going to do it. Take your paper, flip it over on the back, and draw this. Guys, take this. You don't need to write this down, but here's what you're going to draw. Draw this on the back of your paper. Make it probably the width of the page. Make the boxes big enough that you can write words in them. Would have been easier if I just printed this for you, huh? I know. Heaven forbid you'd have to do any work. But guys, copy this into your notes, and then we'll talk about what this is or what it will become. And then it's time for language lessons. But I'll give you a second to scratch it down. I have no idea what this means, but it sounds like you're leaving in a few. I suspect you'll be back, but... Did y'all get it? You need another moment? I'll wait. Brings a tear to me eye. You guys all okay? Okay. Yeah. So let's do that. So you guys can continue to scribble while I explain to you what you're doing. So guys, I think because most of you have had biology, you're probably comfortable, or at least you've heard of the concept of a dichotomous key, right? So di is the prefix for two, and so a dichotomous key basically goes like this. It is a systematic way of categorizing something. So Mr. Maurer probably had you think through dichotomous keys, probably with Jelly Belly jelly beans, because I'm the guy that buys those for him, because I'm the department chair. But you do these things where it's like, does it have feathers? If it does, it's a bird. If it doesn't, it's not. Then does it have fur? If it does, it's a mammal. If it doesn't, it's got to be a fish, because that's all that's left, because that's all I know about biology. But guys, that's a dichotomous key. A dichotomous key is a systematic way of categorizing something using yes or no questions. Now guys, that's what you are going to create right here. You are going to create a dichotomous key. Now guys, look, you'll notice that there are 4 dead ends, right? There's a dead end here, there's a dead end here, and then there are 2 dead ends here. But look, there are 4 things that you are trying to differentiate. The bottom of the pyramid, element, compound, solution, and heterogeneous mixture. So please don't write this down, but watch. Here's what you're going to be thinking about while you're learning the material today. You are going to be coming up with, that's a question mark, you're going to be coming up with yes-no questions. And as you are formulating these yes-no questions, the intent of these questions is to allow you to figure out what things are element, what things are compounds, what are solutions, and what are heterogeneous mixtures. So you'll ask a question. If the answer is yes, then we know what it is. If it's no, then it could be something else. Then we ask another yes-no question. If it's no, then it's this. If it's yes, then it's this. Then another question, and then a yes or no. So guys, the bottom line is you're going to come up with 3 questions. And by applying those 3 questions, it will allow you to figure out what things are elements, compound solutions, or heterogeneous mixtures. Get the idea? Okay, so to do that, flip the paper over. So to do that, the trick is you need to understand what these things are. So guys, the first thing we've got to do is this. We're going to doctor up our, can we just call this a pyramid? Good, pyramid. Guys, first thing we need to do, you see this line right here? Make it go away. Scribble it out. That line don't need to be there. You'll see why in a minute. But guys, now that that line's gone, here's, well, maybe where we should start. Let's familiarize you with the pyramid. So guys, notice along the left-hand margin, it says specific to general. So what that means is at the top of the pyramid, at the top of this pyramid, these are the most general ways to talk about matter, and then as you go down, they get more specific. Does that make sense? Okay. Then left to right, they go from ordered to disordered. So let's see if you understand this. Guys, what is the most specific and yet disordered way to think about matter? Heterogeneous mixtures. What is the most specific, ordered way to think about matter? Elements. And then what is the most general way to think about matter? Matter, right? So let's define matter, shall we? Guys, matter is defined as anything that exists, or here's a little tie back to the previous unit, anything that has mass. So guys, anything that exists, anything that has mass, we understand to be matter. Is that okay? So there's definition number 1. All right. So now, guys, let's see if you really understand the structure of this pyramid. So, guys, up here we have matter, but then let's see if you can figure out the answer to this question. How many different types of matter are there? 2. How do you know? Yeah, because there's 2 boxes down here, so matter can be broken into 2 different types of matter. All right, so you ready? Now, guys, we're going to have a grown-up conversation. You ready? Let's see if we can do this without smirking, but typically we tend to chuckle. Okay, so here we go. When we talk about the 2 different types of matter, we have homogeneous matter and we have heterogeneous matter. Now, guys, in order to understand what that means, let's define the word genus first, and you can just write it off to the side. You'll notice it's hyphenated, so there's a great place to do that. So, guys, the word genus means type. So right next to where it says genus, and this isn't in my notes, but right next to where it says genus, let's write the word type. So guys, in order to understand hetero and homogeneous, we now need to understand hetero and homo. You ready to have the grown-up conversation? Guys, when you think hetero and homo, what comes to mind? Hetero and homosexuals, right? Okay, so if we can figure out from what we know about heterosexuals and homosexuals what homo and hetero means, it should also apply here as well, right? So let's talk about it. If you are a homosexual, who are you interested in? The same. Don't need to write it down yet, but let's keep it in mind. So what then does homo mean? Same. Now do this with me because it's a little different. If you are a heterosexual, who are you interested in? It doesn't mean opposite. So guys, let's talk about it. Here's the reason when we say homosexual or heterosexual, we think opposite. The reason, guys, is because there's only 2 sexes, right? Say, yeah, yes, good, male and female, okay, unless you know something I don't. But there's only 2. So your choices are the one that's like you or the one that's the opposite of you, although it's sort of funny to think of male and female as being opposite and not just different. Because, guys, here's the actual deal, is that if there were 3 sexes, a heterosexual would be interested in either of the other 2. What does that mean? It actually gets to the definition of hetero. Guys, hetero does not mean opposite, it means different. Okay? So, bringing that all together, what is heterogeneous materials? Well, if different types of materials. Good, so let's define it as such. Guys, heterogeneous materials are materials that are made of many types of matter. So guys, let's take that then and let's lend some other terminology to it, and I'll give you examples in a minute, but just watch. So guys, we now understand that heterogeneous means many types of matter. Now some terms. This is the way we are actually going to think about this. Heterogeneous materials contain more than one phase. That is going to be our working lens through which we'll identify heterogeneous materials. Contains more than one phase. So what then is a phase? Well, a phase is a physically separate component of a mixture. I know your hands are about to cramp. Keep going. And then, guys, finally, there's one more term that you need to know, and then I'll let you catch up, and that term is interface. An interface is the place or the plane of contact between distinct phases. So right now, some of you are going, oh my gosh, I'll never catch up. You will. But some of you that are actually thinking as you're writing are now thinking to yourself, what on earth does that mean? I'll show you. And then you'll get it. That's called learning. You guys all caught up? Not yet? How about now? How about now? How much further? Not far now. Do you ever see that Simpsons episode where they're driving across the country and Bart keeps asking the back seat, how much further? Not far now. How much further? No. Okay. Yeah, same idea. You guys good now? Please? Good? Okay. All right, so guys, let's do heterogeneous. You ready? Go Tigers. Here we go. So guys, we got a little bit of yellow, got a little bit of blue. Let's talk about yellow and blue. Yellow is rancid cooking oil. This has been in here a couple years, okay? Blue is actually water with food coloring in it, so you can see it, so it's not colorless. But guys, what we have here is water and oil. Here's an interesting question to tie back to the last unit. Why is the oil on top and not on the bottom? It's less dense. Hey, stuff we learned last unit, right? Okay, so this is an example, guys, of a heterogeneous mixture. What does that mean? Different types of stuff. So let's talk about the different types of stuff. Guys, how many different types of stuff are inside this Erlenmeyer flask? Not 2, not 3, 4. What are the 4? Going from bottom to top, we have water. So this is the water phase. This is the oil phase. This is the air phase. And this is the stopper phase. There are 4 phases inside this Erlenmeyer flask. But guys, the reason that I really love this is as a visual, you can see the interfaces. You see that scum line right there? We're not going to count the scum as a phase. We'll say that where they touch, there we have the oil-water interface. Is that okay? Then here we have the oil-air interface, and here we have the stopper-air interface. So we have 4 phases, 3 interfaces. Do you now understand phases and interfaces? Groovy? All right. So now, guys, let's finish the right-hand side of this chart. So we have heterogeneous materials, but guys, why did we scribble out this line between heterogeneous materials and heterogeneous mixtures? Doesn't it have to be? Guys, if it's heterogeneous, doesn't it have to be a mixture? These are the same. If it's a heterogeneous material, it has to be a mixture. A mixture of water and air and oil and stopper. It's got to be a mixture of stuff in order to be heterogeneous, so this is redundant, so we're just going to get rid of it. Groovy? Okay, so now guys, here's what we're going to do. We are now going to climb back up the triangle, and we are going to jump over to homogeneous. So we understand that hetero means different and homo means the same. So what is homogeneous matter? Materials, what is it? Same type of matter the whole way through, but guys, do this with me. Rather than writing same type of matter, could you come up with a definition that includes the word phase? Contains one phase. That's it. So guys, homogeneous matter contains only one phase. Is that okay? Okay, so guys, if that is homogeneous matter, then how many different types of homogeneous matter are there? Do you see it? There's 2. One of these is called a homogeneous mixture, and then the other is called a substance. So guys, let's go down here first to homogeneous mixture. Guys, we are just going to call these solutions. So circle the word solution, and allow me to make one of these for you, and then let's talk. Okay. So guys, here we go. We understand some stuff about this, right? Is this homo or heterogeneous? Heterogeneous, so it contains phases and interfaces. Good? Okay, now let's do this. Guys, give me the benefit of the doubt that this is distilled water. It's not. It's tap water. It's already got stuff in it. Let's pretend. And then, guys, here's what we're going to do. We are now going to make another mixture. Are you guys okay with the idea that this is a mixture? Because it's got to be, right, if it's heterogeneous. Now I'm going to make another mixture. I'm going to put some table salt in here. I'm going to get my stirring pencil. And I'm going to stir this up. And the salt dissolves. And now the salt is all gone. And now I have another mixture. Yeah? So let's talk. Homo or heterogeneous? Homo or heterogeneous? Wait, but it's a mixture. Okay, now we're in a little bit of a gray area, right? So guys, let's see if we can wiggle our way out of the gray area by going back to this. We understand that this is heterogeneous, and we've called it a mixture, although I would argue with you this isn't very mixed up. It seems pretty unmixed because you can see it. How about now? Let's mix up our mixture, shall we? So guys, as we mix up our mixture, and some of you are having a magic moment realizing that in fact yellow and blue do make green. There you go. Yes. Guys, in addition to that, you may now be wondering, is this still heterogeneous? So let's talk. Is this still heterogeneous? Is it more than one phase? Does it contain interfaces? Guys, it does. And if you don't believe me, watch. What happens if I set that down? Well, here, you can't see. What happens if I stop wiggling it? It's going to separate. So we are going to end up again with the water phase on the bottom and the oil phase above it. Now, guys, if the simple act of stopping shaking it allows those phases to recollect, do you suppose those separate phases are still present while I'm shaking it? Absolutely. They are just more distributed throughout the mixture, but guys, those phases and interfaces still exist. Now contrast that with this. Are these two mixtures fundamentally the same? Salt water and oil in water. How are they different? Salt mixes, but so does this. But it doesn't separate. So guys, let's do this. If I were to set both of these down, and assuming we could cover this so the water doesn't dissolve, or the water doesn't evaporate, if we come back in a week, what are we going to end up with here? It ain't going to change. Will the salt ever fall to the bottom of the beaker? But what if we come back here in an hour? It's re-separated. So guys, there is something fundamentally different about this mixture as compared to this mixture. Ooh. And I know that most of you are onto it, that this is heterogeneous and this is homogeneous. We call it a solution. But guys, let's talk about how fundamentally they're different. And this sounds really corny, but to visualize it, imagine you could do this. Imagine that you could shrink yourself down, super small chemistry guy size. This is nasty. And you could scuba dive through this. Have you all seen Ant-Man? Similar idea. Okay, so you're like Ant-Man scuba diving through this. So guys, as you're scuba diving through this, what are you going to encounter? Well, it's going to be water, oil, oil, water, water, oil, oil, water, right? You're going to run into globs of oil. You're going to run into pockets of water, and it's going to be all goopy and yucky. But guys, as you swim through this, is it going to be water, water, salt, salt, water, salt, water, salt, water? What's it going to be? It's going to be salt water the whole way through. So guys, if this is salt water the whole way through, how many phases does it contain? One, and what is that phase? Salt water, and because it contains one phase, is it hetero or homogeneous? Homogeneous, and what do we call that? A solution. Do you understand the difference? So guys, the idea is this. What do these have in common? They are both mixtures. Guys, pay attention because here's a question for the back of your sheet. Don't flip it over, but let's think about it. So guys, these are both mixtures, right? Okay. But this is a heterogeneous mixture and this is a homogeneous mixture. How do you tell a homogeneous mixture from a heterogeneous mixture? What's the distinction? This has phases and interfaces, and this does not. Or what about this? Does this separate? Does this separate? Does this? Things to think about as we start doing questions. Yeah? That's a good question, and we're fighting with this in my AP class right now, because what you're talking about is defining our system. So if you were to also, okay, so let's do this. You ready? Let's consider everything inside the beaker. Now is it hetero or homogeneous? It's hetero, because now we've got a saltwater phase and an air phase, and that would make it heterogeneous. This is a bad idea. But if I mix them up, then they sort of mix and then they settle again, right? So in fact, that would be heterogeneous. But if we're just focusing on the saltwater, are you okay with that being homogeneous? Is that okay? All right. So you okay with hetero and homogeneous? You okay? And then, guys, you understand that there can be heterogeneous mixtures, and those always contain phases and interfaces. And what about their ability to separate? Do they separate? They do. Then, guys, we've got homogeneous mixtures that do not contain interfaces. They're all one phase, and do they separate on their own means? They do not. Okay, you good to there? All right. So then, guys, let's flesh out solutions a little bit more. There's two terms that you need to know. So, guys, again, the solution we're talking about is salt water, yeah? Okay. The two terms you need to know then are these. First of all, well, they're both there. Solute and solvent. So, guys, the solute is the thing that is being dissolved, the dissolvee. In the case of our example, it's the salt. And then the solvent is the dissolver. In the case of our example, the water. Those are terms you just need to know. We'll be using them throughout the year. All right, so guys, here's where we are. Matter is anything that exists. There are two kinds of matter. There's heterogeneous matter and there's homogeneous matter. Heterogeneous matter is a mixture of things that has phases and interfaces. Homogeneous matter is the same stuff the whole way through, but it could still be a mixture. But if it is a mixture, it can't be a mixture that separates, and we call it a solution, because these mixtures are the same thing the whole way through, unlike oil and water. Yeah? All right. Questions there? Okay. Then, guys, the last thing we need to do is substances. And the first thing that I'd like to do is define it for you. A substance is a type of matter that has unique physical and chemical properties. What does that mean? We'll talk in a minute. But guys, it's important to realize substances are also homogeneous. They're the same thing the whole way through. Notice that substances are also under homogeneous. So substances are also homogeneous. The thing that's interesting about them is they have unique physical and chemical properties. So what does that mean? Let's differentiate this. Is that an okay word to use with y'all? Let's see how this is different from a solution. So guys, this is a solution. What does it look like? What does it taste like? It ain't nasty. It's not unique. It looks like water and tastes like salt. This is not unique. It looks like water and tastes like salt. Therefore, it is not a substance. It does not have unique properties. It has the properties of the things that make it up. Therefore, it is homogeneous, but it's not a substance because it's not unique. Okay? So now let's talk about what it means to be unique. You ready? What are physical and chemical properties? This is going to go right up here. Guys, a chemical property, and this is the lab that we're going to do on Thursday. A chemical property can only be observed. I'll zoom into this. A chemical property can only be observed by creating a new substance. A physical property does not require the creation of a new substance in order to observe it. No new substance. Your parents are really going to the concert tonight? I kind of feel like a dork, like admitting that I'm going to a concert that your all's parents are going to, but at the same time, I think it's kind of cool. I'm slowly coming to terms with the fact that I am now old enough to be some of your parents. I'm like an adult. You guys done? Not yet? Please. All right, I'll wait. You good now? Yeah? Good? Okay. So, guys, let's do this then. What on earth does this mean? Ready? Play along at home. Actually, don't. What does this mean? Ready? Piece of paper. You would all agree. Piece of paper. Now, I am going to reveal to you some of the properties of paper. I know, right? I feel like Mr. Ellingford. And then you're going to tell me if that's a physical or a chemical property. Ready? Watch close. Many of you didn't know that paper can rip. No, I know. Now, is this still paper? What about this? Yeah, so paper rips. Is that a physical or a chemical property? Physical, because in determining that, we didn't make something new. Paper crumples. Also true. Physical or chemical property, is that still paper? Did we create something new? Physical property. Now, what about this? Guess what else we know about paper? Paper burns. Now, guys, as the paper burns, wait, oh. Is that paper? Is that paper? Right there? Wait, is this paper? See, you weren't as excited about tear and crumple, but all of a sudden fire is really turning your world on its ear. So, guys, right, smoke. Yeah, so is ash paper? Hang on, guys, listen, you're going to learn if you listen. So, guys, is ash paper? Is smoke paper? Now, but wait, is there ash trapped inside of paper? Is there smoke trapped inside of paper? So when we determined that paper burns, did we create new things? We created smoke and ash, which were not present previously. Because we created something new, paper burns is what kind of property? Chemical property. Why was that exciting? Okay, hold on, guys. Okay, I'm glad. Go ahead. Hang on, guys. Yeah, so what does that mean? So you understand what a physical and chemical property is, right? But the question is what does it mean for them to be unique? And so let's bring it back to our simple example now, and I'll show you a better example in a minute. So for example, what are the chemical properties of water? Well, it's a liquid. Well, I'm sorry, water, let's do it. Never done this before. Let's do it. Water is a liquid, physical or chemical property. You can study that without changing it, right? What about water can be broken into hydrogen and oxygen? You may know that water is H2O. So we can take water and pass a current through it and break it into hydrogen and oxygen. Physical or chemical property? It's actually chemical because the hydrogen and oxygen gas wasn't there before. It was tied up as water. So we can talk about these unique physical and chemical properties. Now, what about the properties of salt? It's a white crystalline substance. It tastes like salt, those sorts of things. But when we mix these together and make salt water, it's not unique. Its properties are a combining of the properties of water and salt, so it's not unique. Is that okay? I'm going to show you more about this in just a minute, but there's one other thing I've got to do before I can. So guys, are you okay on the idea of physical and chemical properties? Because again, guys, this is the lab on Thursday. You got to get this down. You're good? Okay, so now guys, let's go down here. And we're going to talk about the two types of substances. So what does it mean that there are two types of substances? That means there's only two kinds of stuff on this planet that has unique physical and chemical properties. The first one is elements. So what is an element? An element is composed, I'm going to turn the lights back on. An element is composed of one type of atom. Now guys, you ready? How many different kinds of elements are there in the universe? All right, here we go. So our periodic table goes up to 118, but that is not the answer. The reason, guys, is because the universe actually only got to uranium. Uranium is the heaviest element that exists in the universe. So if you were to ask the question, how many different types of elements exist in the universe, the answer is 92. Maybe we should talk, where do the atoms come from? Do you guys know? Where did they come from? This isn't a creation or evolution thing. We actually know the answer. I certainly believe in, I'm going to tell you anyway. I believe in creation. But I also believe that things are changing and there's science to explain it. So guys, where did all these elements come from? Do you not know? Stars. We'll talk more about it in the next unit. Every single atom that's not true. Every single atom with the exception of hydrogen and some helium, those are the two lightest elements. Guys, with the exception of hydrogen and some helium, all of these other elements were created in stars. We'll talk about how that happens in a couple weeks. But guys, the universe only got to uranium element number 92, so where did all the rest of them come from? California. Seriously, there's well, not anymore, but originally they came from California. Thus we have things like berkelium and californium and americium, America. Guys, it turns out that all of these heavier elements were made in laboratories initially in California. Well, plutonium was actually made during the war effort, and that was made in Tennessee. But guys, most of these elements were made in America, literally, most of them in Berkeley, California. And then once things really started to heat up, some of these other heavier elements were made in Russia. But all of these elements from 93 through 118 were actually made in labs at universities. So there you have it. But what do they all have in common? And guys, the answer is this. They all contain only one kind of atom. So guys, if you've got sulfur, this is sulfur, this is it. This is what pure sulfur looks like. Guys, and you're all saying, guys, sulfur doesn't stink. I don't know if you know that or not. Hydrogen sulfide, which is hydrogen and sulfur bonded together, that stinks. That's the rotten egg smell. Sulfur doesn't smell at all. So guys, this is what pure sulfur looks like. What do all the atoms inside this beaker all have in common? They are all sulfur atoms. Now, what do all of those atoms have in common? Do any of you know? What does it mean that sulfur is element 16? The number of protons. So guys, every single atom inside here, every single one of those atoms has 16 protons. If it didn't, it wouldn't be sulfur. Guys, this is pure copper. What do all of these atoms have in common? They're all copper. How many protons do they all have? 29. If they had any more or less than that, they wouldn't be copper. Get the idea? Now guys, what about this? What about the chunk of lead that you guys found the density of, or not, in lab or on the test? Those are all lead atoms, element 82. Now guys, here's the crazy thing. If we could pull 3 protons off those atoms, what does it turn into? Gold. That's the only difference between an atom of lead and an atom of gold is 3 protons. And we can do that without a whole lot of hassle. I can't, but there are labs where they can pull those 3 protons out of lead and turn it into gold. Yeah, pretty crazy, right? Okay. So guys, you get the idea, I think, behind atoms. Now let's go over here and let's talk about compounds. What is a compound? So guys, compounds are 2 or more elements bonded together. That's like a great example. Hydrogen is an element, oxygen is an element, bond them together, you get water. And water is nothing like hydrogen or oxygen. Good, great example. By the way, guys, I know I sort of laid this out there and I meant to mention this. You understand that all the elements in the universe except for hydrogen and some helium came from the stars? Where did all the hydrogen come from? The Big Bang. And we'll talk more about that later. Okay, you guys, do you at least have that written down? You're okay? All right. So this is actually, Tatum, what I wanted to show you. But here's the deal, guys. So elements and compounds, you ready? Do this with me in your head. Elements and compounds, what do they have in common? They are all substances. What is it that makes something a substance? They are, yes, but they are unique, right? So all substances are unique. So guys, let me show you unique. You ready? Sodium. Sodium is an element. If you find it on the periodic table, it is element number 11. This is what pure sodium looks like. Pure sodium is a bright, shiny metal. It is very soft. You can cut it with a butter knife. But guys, the thing that makes sodium really interesting is it actually burns on contact with water.
Sodium metal in?
All that is a chunk of sodium in a beaker of water.
So that's fire on top of water there. Little flame there. It's a ball here, you'll notice, round shape there. And that's because it has melted, and so that's actually molten metal there rolling around the surface. And notice it's all gone there when it's all reacting.
Okay, so guys, do this with me. What are the physical properties of sodium? It's shiny. It's a soft. So you can cut it. Is it still sodium? Can you see that it's shiny without turning it into something new? What else are the physical properties of sodium? It's a metal. Is that okay? What are the chemical properties of sodium? Reacts with water and bursts into flames. Guys, as it was burning, was that still sodium? No, there were sparks and gas and all other stuff. That's a chemical property of sodium. You okay? Okay. Now, guys, let me introduce you to another element. Some of you see where this is going. This is chlorine gas. Guys, chlorine gas, element number 17. So what do all these atoms have in common? 17 protons. Guys, chlorine gas, just from looking at it from a distance, well, in a picture, what are the physical properties of chlorine gas? It's yellow. It's a gas. But guys, chemical properties of chlorine, you okay? Guys, chemical properties of chlorine, you ready? We have to surrender the high ground on this as a country. Guys, we all have this idea that Americans are sort of pure and out in the world just trying to do good, right? You understand who came up with the idea of weapons of mass destruction and biological warfare and all that stuff that we went into Iraq for? It was us. Guys, in World War I, we were the people that actually started this idea of chemical warfare. And this was it. We actually used to drop chlorine bombs. You've heard of mustard gas. Guys, we actually used to drop chlorine bombs on enemy troops as they were hunkered down in the trenches during World War I. And don't look it up. To see somebody die of mustard gas inhalation, what you're actually watching is the chlorine gas ripping their cells apart and killing them slowly. But guys, it's horrible. So, I mean, besides the political implications of that, guys, not only is chlorine a brown gas, a yellow gas, and a gas, but chemically it's deadly. This is horrible, awful, yucky, kill you, no screwing around stuff, all right? Okay, so we understand some of the physical and chemical properties of sodium. You good? Physical and chemical properties of chlorine, you good? But now, guys, what happens when we bring these two things together? We get table salt. And guys, watch. I can actually show you how it works. You ready? This is how to make table salt. Please don't walk out of here thinking that this is how we get. Do you guys know where we get this table salt? Out of the Great Salt Lake. A lot of it is. They actually go out there and but you can make your own. You ready?
This is one of my favorite experiments. Supposing you want some fresh salt. None of that's...
Oh, crap. I meant to pause because I love the idea of fresh salt. As if that stuff is, no.
This is one of my favorite experiments. Supposing you want some fresh salt. None of that stale old store-bought stuff. You want the fresh stuff.
So, guys, how are you going to make salt? We're going to put sodium and chlorine together. But, guys, let's think about this. You know about sodium, right? Guys, think about the things you know about sodium. You know about chlorine? Table salt. Is it anything like sodium? Is it shiny? Is it a metal? Does it burst into flames when you throw it in water? Is it anything like chlorine? Is it a gas? Is it yellow? Does it kill people? No. So when we bring this together, we've created, be careful guys, don't get distracted. We've created a new substance. And here's how it goes.
You got to make it yourself. Well, how are you going to do that? Salt is sodium chloride.
So there's sodium, and here's chlorine in a container. Here's popcorn.
Is a metal that explodes on contact with water, and chlorine is a deadly poison gas. They actually used it in World War I as a poison gas.
So guys, here's what we've got. We've got a canister of chlorine with a hose that is then blowing chlorine gas into this, actually a crucible, an evaporating dish. And then in there is a chunk of sodium, and he's lighting it on fire, and then up here's a bag of popcorn.
Take a bowl full of molten sodium and you blow pure chlorine gas into it.
So guys, what we're doing is we are burning sodium metal in a stream of chlorine gas. So what's this stuff up here? The smoke from this fire is table salt.
You got a fire, and the smoke coming off of that is pure salt. So we hung some popcorn over it. You know, salt the popcorn with nice fresh salt.
So there you go. That's how to salt popcorn with fresh salt. Until, watch what happens.
And it worked great. We got some good shots that we used in the magazine. Then, turns out, the net started melting, and it actually dropped the popcorn into the molten sodium. Sodium exploded, and we got popcorn and sodium flying everywhere. That's really not such a bad thing. It tells you that science doesn't always go the way it's supposed to. It tells you why it's important to wear a face shield and have all the right safety. And we got popcorn and sodium flying, so we hung some popcorn over it.
Okay, so now guys, let's talk. Here we can see the table salt, right? Here we can see the table salt. Is this anything like sodium? Is this anything like chlorine? Is it unique? Yes, but is it an element? No. It is a combination of the elements sodium and chlorine bonded together. So while it is unique, it is not an element. So what therefore is it? A compound. You get the idea? All right.
You know, salt the popcorn with nice fresh salt. And it worked great. We got some good shots that we used in the magazine. Then, turns out, the net started melting, and it actually dropped the popcorn into the molten sodium. Sodium exploded, and we got popcorn and sodium flying everywhere. That's really not such a bad thing. It tells you that science doesn't always go the way it's supposed to. It tells you why it's important to wear a face shield and have all the right safety equipment. And it made some really good shots that we could use also.
All right, guys. The rubber's going to hit the road. Here we go. Let's see if together we can come up with a solution to the that was bad. No pun intended. A way to flesh out our chart.
So guys,
again, on these horizontal lines, we are going to ask three questions. Those questions will be yes/no questions, and as a result of each of those yes/no questions, we've got to be able to tell the difference between elements, compounds, or heterogeneous mixtures. Now, some of you are starting to pick up on the idea that this. It's funny if you look at it from a distance, you can kind of see it. See how this is sort of pyramid-like? Yeah, right. So guys, maybe because this is like our pyramid, we can come up with questions that would allow us to break these down similar to the way our pyramid is broken down. So if we wanted to do that, guys, you'll notice this starts the same place as our pyramid. Matter? And it first gets broken into what? Homo and heterogeneous. So what is a question that we could ask that would allow us to tell if something's hetero or homo? Go ahead. Oh, sorry, go ahead. Does it have interfaces? Okay. So, and guys, hold on, Sergio. There isn't one right or wrong answer, but if the question was, does it have interfaces, then you've got to figure out where the yes and the no goes. So if you want to go with, does it have interfaces, where are you going to put the no? Where are you going to put the no? On the right or the left? So if it doesn't have interfaces, what does that make it? Homogeneous. And if it does have interfaces, it would be hetero, and that's a dead end. Sergio, what were you thinking?
I take back what I was going to say.
Okay, go ahead, Tina. Oh, good. Okay, so does it have one phase? Now, but does that switch your yes and no? So, how did you say, does it have one phase? If the answer is no, then it's hetero. If the answer is yes, then it's homo. Go ahead, you have another one? I like that one. Can it be separated? But now we've got to be careful because the question is, how is it separated? And we need to add the term by physical means, because there are some chemical things we can separate as well. What about this? Can it be separated without creating something new? 23 years of this, and that never came to me before now. Can it be separated without creating something new? Because that ties back to physical and chemical change. So can it be separated without creating something new? If the answer is yes, it's hetero. If it's no, it's homo. So however you want to tackle that first question, now we need to drill down into homogeneous. So what could we ask that would allow us to differentiate, tell the difference between the homogeneous things? What do you think? What you got? How could we differentiate? Could be. I actually do it a little differently. But you could. We're just trying to break down homogeneous. How could we start to tease apart homogeneous? Yeah, go ahead. Okay, so maybe the question is it unique from the things that make it up? Okay, so Marilyn, if you said, okay, so you know what? I could actually be writing this down, I guess. So but again, people are going different directions, but I think we've all settled on the idea that this is homo and this is hetero, however you got there. So Marilyn, your question is it unique? So I'm just going to write down the word unique. Okay, so how would you tease that apart? So what does that differentiate between? Substance and solution. So which one's going to be your dead end? Okay, so if solution is your dead end, then would that be a yes or a no? that would be a no. And then this then would be your yes. And if you went that way, what does that make this? A substance. Okay, I feel okay about that. Then guys, now we need to get substances apart. What's a question we could ask? Yeah. Okay, so does it have more than one element? And if the answer is yes, it's a compound. If it's no, it's an element. Okay. Other questions? See, I like to be practical about this one. Is it on the periodic table? It's up to you. But guys, however you choose to tackle that, and are there any others you want to throw out for consideration? You okay? Guys, here's what I would encourage you to do first. Grab your homework and start with number 11. Stress test number 11. See if you can distinguish between heterogeneous mixtures and solutions. That'll at least give you your first question. And then guys, notice where this homework assignment literally takes you. Look at number 13. Guys, you're headed home, and literally your homework needs to be done at home. You're going to don't tear apart. You're going to rummage through your kitchen, your pantry, your bathroom, wherever you've got cleaning supplies. And guys, you are going to find 3 examples of elements, compounds, and solutions at home. And come back with what those examples are and where you found them. Yeah. 3 of each. Thus the 3 lines under each one. Yep. So guys, we have about 15 minutes left. Is there anything else you want to explore relative to all of this? You're good? Okay. So homework, we'll grade this Thursday. We will do another lab on Thursday. I'm going to duck out for a second and wash my hands because they're all full of ash. And guys, we'll go when the bell rings. The rest of the time is yours. If everything goes well and the creek don't rise, I'll have your test for you on Thursday. And that'll do us.